Welcome to this talk about how to attack a power plant and stay alive. Now I'm going to tell you a little about me and about this talk. I'm a researcher with Checkmate. My areas of interest include machine learning, reverse engineering, cryptography. My areas of interest do not include power plants, actually, usually at least, so this is not really going to be a technical talk. If you had seen the speaker list for this event, you may have seen me listed as an expert on industrial and control system security. Well, I guess the main takeaway from this is don't believe everything you read on the internet. But you know, I'm still standing here and I have to tell you how to attack a power plant, even though I know basically nothing about this subject. So let's proceed to the only way forward possible. How am I going to attack this power plant? So I Google it and I quickly find this site called Anypedia, which gives me a nice list of power plants in Europe classified by type of power plant. Some of them are nuclear power plants, others are powered by coal, and others are powered by gas. Now, and this is important for the sake of this presentation, I am a person who really hates gas-powered power plants. With a passion. I want to see them brought down and I want to see the prices of oil rise for some reason. So let's zoom in to Spain and let's pick a gas-powered power plant near to us. The Sagunto power plant is the closest gas-powered power plant to here, if I'm not mistaken. And a quick trip to Wikipedia, and I find all of sorts of statistics, basic statistics about this power plant. I find that it was commissioned about 10 years ago. I find that its output is about 1,200 megawatts, and all sorts of information like that. Also, from Google Earth, I can get a nice bird's eye view of this power plant, and from Google Street View, I can see the entrance and the parking lot, which may figure into this later somehow. So all of that is well and nice, but I can't attack the power plant based on how it looks from the outside and all of those basic statistics. I'm interested in what's going on inside. Now, first of all, if I'm interested in what's going on inside, maybe I'm also interested in who is going on inside. So suppose I go to LinkedIn and I search for Union Fenosa, they operate this power plant, and I limit my search to the Madrid area in Spain, and I have here 1,500 results, and some of them, I imagine, work at this power plant. So now maybe I have some names, maybe I have some job titles, maybe I have some email addresses, could come in handy later. And as I said, I don't know much about how industrial networks are put together, so I go to Google and I find this nice schematic that gives me a general idea of what I can expect. I mean, at the top we have the resource management layer where most administrative workers are engaged. Below that we have the MES layer that manages the shop floor, connecting to the SCADA layer. SCADA, I've heard that word, right? I think it's important. Below that we have the programmable logic controller layer, which actually sends electrical surges and directly manipulates the instruments on the field. Okay, so like this is a general schematic. You can't attack a general schematic. But you know what? Have you heard of Schneider Electric? They manufacture equipment, and their equipment is used often in contexts such as this. And for the sake of this presentation, we're going to assume that the power plant uses equipment by Schneider Electric. That's not necessarily true, but this assumption, while we're making it, it will become clearer later. So even if we're making this assumption, and even if it is borne out and turns out to be correct, how can we base an attack on that? I mean, in order to base an attack on that, we are going to have to know how Schneider Electric sees and advises the correct way to take all of their equipment and put it together and create a power plant network. I mean, it's not like if you went to a trip on the internet, you can find like this list of slides on SlideShare that gave you this, that's useful. Somehow we ran across that, and now we have a general idea, an approximate map of what we can expect if we find ourselves inside of this power plant's network. So first we're going to have to establish some kind of foothold in order to advance, in order to make our attack succeed. So on the previous talk you heard about phishing and fraudulent emails and how common this is. So suppose I send an email to one of the employees. I have some names and email addresses, remember. And I send them a quick email asking them to look into the attachment because it has details about their annual performance review. Now, as you can see, the attachment is a .doc.js file. It may look like a kind of document, but no, really, it's not a document. And if you actually open this attachment, it's going to run code on your machine. But surprisingly, people are generally less aware of this than of executable files. By now, people know that if they get an executable file in their email, they should think twice about opening it. But somehow with JS files, it's less of a clear-cut thing on the matter of awareness. And in fact, in the past few months, we've seen like a surge of malware riding exactly on this vector. So this is one way that we could get in. And alternately, we could maybe take a USB drive and put our malware on it and put the Union Fenosa logo also on it and lob it across the fence into the parking lot and wait. Now, at this point, you're asking me, Ben, what? Really? Do people really plug in every USB drive that they just find lying around the parking lot? Well, a few months ago, a few guys from the University of Illinois conducted a research to check exactly this. They spread some USB sticks around college campus and waited to see what would happen. And they managed to get, like, between, depending on the circumstances, between half and every single USB drive, like 98% success rate of these drives attached by people to their machines. And the typical time for the USB drive to be connected to the machine was like around 6 hours, but in some truly degenerate cases, the time from dropping the USB stick on the floor to it being plugged into the machine was 6 minutes. 6 minutes, that's really something. So at this point, one way or the other, we have established a foothold in the ERP network, right? So what are we going to do next? I mean, we are going to look around, we are going to see if the network topology matches what we expect to find based on the approximate map that we saw before. And we're going to report home to our established CNC server so we can, we standing back at base can actually see those results. But once that phase is done and assuming that everything is in order, we're going to want to decide on our next step. Because we are a ERP network, but that's not enough. We want to move like downwards in this diagram. The question is downwards to where? Well, looking at this complex diagram, I eventually find this. What's this? It reads supervision, looks important, it has a nice logo next to it. So a quick search tells me that this is called the VideoCitect. There is no chance that I just pronounced that correctly. VideoCitect is a SCADA solution, basically. And I know enough to realize that if I can take control of this thing, then it is basically game over. That's going to be the flop of my attack, right? So this is our next move, right? It looks so simple. There's this arrow from the ERP network to the SCADA solution, but wait just a minute. Let's zoom in some more. What's this in the middle of our arrow? What's this? Enhance? Oh, it's a firewall. Okay, well, I work at Checkpoint Zoom. You may expect me to stand here and tell you that the firewall is going to clearly magically block this attack because you know it's a firewall and firewalls break everything. But fortunately for me, this particular firewall is not even made by Checkpoint, so I don't have to stand here and tell you that. But in any way, firewalls are good at what firewalls do, but firewalls are not magic. I mean, for instance, if you have an incoming software update, I mean, it's not at all obvious that a firewall can or should be able to look at a software update, for instance, for a SCADA management solution, and reverse engineer it on the fly and come to the conclusion that it is malicious. That's, you know, firewalls, they know to do what we program into them, to the power of discernment that we are able to give them. And we work all the time to make them better. but sometimes there are things that you just can't do or won't do. So this is one vector of attack that we could try, just to play nice with the VGOS detect and using its correct, legit built-in functionality to manipulate it. So that's one thing. Another idea is that we have the ability to send packets, so maybe we won't play nice with the VGOS detect, maybe we'll force its hand. I mean, we have access to it, so if I look at what this VGOS detect thing is built on, once it's running, it has built in something called Microsoft Internet Information Services. So let's write Internet Information Services. So I run this thing through a vulnerability database, and I found out that there have been like 5,000 different vulnerabilities discovered for this thing in history. So, you know, what could possibly go wrong, right? I mean, a lot of those vulnerabilities are probably patched, but you just heard last talk about patching and the problems that go with it, especially in critical infrastructure such as this, where people are deathly afraid of any downtime, and the instruments are difficult to get at. Actually, this is where a firewall is much more equipped to help you, right? Because exploits are much more constrained in how they're going to appear. And if you have a firewall with updated definitions that knows to look for that exploit, then hey, it may stop it in transit. So that could happen. I mean, just to give you a taste of what I'm talking about, in 2010 they discovered this vulnerability that allows a remote attacker to completely take control of an IIS server by basically sneezing at it, or this vulnerability from 2013 that allows an attacker to take complete control of such a server by basically looking at it funny. And those are for 2010 and 2014. Who knows what they're going to discover tomorrow, yes? So at this point, one way or the other, we have gained control of the VGOS detect server. And from this point on, it's not a question of whether we're going to be able to do damage. It's a question of how much damage we will be able to do. You have heard of Stuxnet. Stuxnet what it did was send very specific commands to turbines to spin quickly and then spin slowly again, eventually destroying them because they were not designed to operate that way. And all the while, it took control of the human-machine interfaces such that when anyone was looking from the outside at the human-machine interface, they saw business as usual. So if you don't just rush all in and send a command, destroy everything, but you're more subtle, you may be able to destroy everything eventually. So all of this is nice, but at this point you're telling me, look, Ben, all of this is nice in theory, but you can't really expect all of this to be relevant to the real world, right? Because you just went Googling and assembled this like generic sounding attack plan, and you built this castle in the sky. How is this relevant to the real world? There is one thing I have not been entirely truthful with you about. This entire attack plan, it was not actually conceived by me putting together step by step by looking at Google results and slides from SlideShare and whatnot. This is actually a real attack plan conceived by a foreign hostile actor around 2013, 2.5 years ago, more or less, with the intent to destroy gas-powered power plants in Europe. You can see the front page. You can see the various related CVEs and all the little checklists that need to be ticked in order for the attack to go through. And you can see the very diagram, more or less, that we worked with. So before I say thank you and I'm done with this, I'm going to have to say what the takeaway from this is. Because this is just one document. And we put our hands on it somehow, and we don't know if it ever reached fruition, whether they even executed it at the end. But this is just one document, and imagine how many others like it are floating around and waiting for their day in the limelight. And imagine all the little decisions, security policy decisions, that are going to make the difference at every point of the attack that has been outlined. A small decision could mean the difference between this attack reaching the perimeter and bouncing off harmlessly to this attack going all the way through and destroying the power plant. So with this in mind, let's make sure to make all the correct decisions so that if and when a plan such as this is shifted into gear, it fails sooner rather than later. Thank you. And are there any questions?